I will start our presentation to 3D printing for insulation elements from bioorganic biofibers. I'm from the GNS GmbH. I'm a chemist and a CIO. And I want to say something about our motivation. It was a rethinking of building materials and sources. On the one hand, we have the new European Bauhaus call for sustainable building materials and design. And also on the other hand, we have the EU demand to have more than 42% from renewable energy sources in future. And so we have thought about building materials from bioorganic residual materials like bioorganic fibers. Okay. Biofibers as building material for insulation panels have history, and you see at the left side the past where biological materials were used. In the present, we have often the styrofoam materials, and maybe in future we can have new materials from residues, from organic residues. We want to combine the bio-based and the degradable character from the past with the easy installation from present, and additional, we have a new effect that we can be freedom of design with 3D printing. What our biofibers come from? This is a sustainable byproduct from the agricultural circular economy. It means it comes, we grow biomass, we make food, we have then waste, and after this we can process this in a biogas plant where biogas is produced, bioenergy. But then we have a digestate, and the digestate is used as a fertilizer. But we have much emissions from this fertilizer, and so we remove with our technology the nitrogen and other fertilizers to get a low emission fertilizer for agriculture, and what we remain is a non-digestible residue fiber. It is wood-like, like a lignocellulose. Something about the GNS, because we have developed this process. GNS from Halle an der Saale. We are experts in natural waste material utilization, from environmental technology to energetic use to material use. Like this recovery of nutrients, so we have developed this digestate treatment system, GNS Fiber Plus called, and then we have developed a product line, Magaverde Biofiber Products. This is realized in a big scale at a big biogas plant, Benas Biopower, since 2016. The first products like paper, boards, and pulp materials we have then realized to 2019, and then he has realized his own production with paper production. And you can see here at first the cleaned organic fibers, the dried organic fibers, then it must be refined as a small that is spliced, and then you can use it in a paper production, pulp production, and we have also used it in wood materials. And now we go to the next step, to materials passed to 3D printing. Here you can see, I have forgotten, Magaverde is our trade name. It means magic green products. It's also the German word Erde, from earth, use, and to earth, back again. And we have said we only use natural materials, no dangerous chemicals, so it is fully degradable, it's building humus, and it's approved for organic farming. And so we have developed, for instance, mulch mats and papers in agriculture, horticulture, to avoid here the pesticides and herbicides. We have used it in packing materials and cardboards, but it is two-dimensional. And now we go to the next step since 2023 to develop biofiber paste, genau, paste. We also only use natural components for this, native 3 components materials mixed of the fibers, biogenic polymer and native minerals and some additives. You all can found in household, kitchen, etc. And only we then use a catalytically controlled cross-linking with small pieces of not dangerous catalytic material. What you, oh, that's not the right.
Just a bit shifted, yeah.
Yes, it is not good to see. This we have done a lot of experiments in lab scale, over 100 experiments. It is not the right photos. You can see only some pieces from this. We have wet fibers. We have then mixed the components together and then produced the pasta here in lab scale. And we have made an iterative process to add materials, minerals, which is binding properties, additions of catalysts, and so we could adapt the viscosity of the biogenic printing paste to have the best drying properties, and so we have improved it step by step, and then Mr. Feldmann could use it for his 3D printing.
Yeah. Yeah, welcome also from my side. My name is Jakob Feldmann from Additivum. Let me quickly introduce what Additivum is. We are a small and young company specializing in ceramic and clay 3D printing. About 4 years old with a team of 6, so still fairly small, based in Darmstadt, Germany, just around the corner. We do industrial additive manufacturing of ceramics, of clays. The video played once at least. We do our own designs and sell them, so we sell the goods, but also do commissioned work. So if someone comes up with a crazy idea, we do our best to fulfill that. And we specialize especially in making single items, but also larger series of products. I wanted to talk a bit about ceramic 3D printing because it has a bit to do with what we did in that project. You can only print if you have a printer. The printers we found were not really suited for our needs, so we started designing and building our own. So especially my job is actually the engineering part of building the printers. But it's not just that. It's the there you can see me working on one. The digital design process and digital pre-processing, of course, also using Rhino and Grasshopper, as everyone else. And a big step and a big part is the material preparation and handling, especially clay. You cannot just buy a roll of filament, which is nice and easy to do. If we want to produce every day, or every week a couple hundred items clay printed, we need to really know how to deal and keep a consistent viscosity and moisture, for example, of our clay. And this is a big part of my job as well. But there's also a lot that comes after the actual printing part, such as drying and firing of the parts, post-processing, glazing, and so on. And this allows us to produce in ever-rising quantities and qualities. And the niche we're actually the most successful in, I brought one just for you to see what weird things you can 3D print, is urns. So we produce almost 200 urns per week. We also do other stuff, but this is the main focus we have right now. But maybe this changes with this project. But just so you have an idea how that looks like. And actually all of us end up in one of those. All right. All right, how does this now fit together with what Mrs. Bauermeister just mentioned? We figured if we have a paste which is clay-like, we could also just try to print that. So we filled our machines with this. And at the beginning, I have to tell you that it was a sticky mess. It for some reason, stick to everything, to the cartridges, to the conveying system, to everything but the build platform. So it was a huge mess, but we managed to get it under control by adding more fiber volume, especially shorter fractions of fibers. This increased the viscosity of it and also made it less tacky. But we also have other advantages by this. The whole print gets more and more stable by adding more fibers. So we encountered the problem, as shown in the video before, that the parts of the still soft material collapse under their own weight, and this got much better by adding more fibers, especially shorter ones. As I mentioned, reduced tackiness, increased thixotropy, so inside the nozzle everything is still fairly liquid, and once it's stationary and placed, it stays put. But we also increased the mechanical properties of the material, so it got harder and firmer after printing and a better surface finish. The only downside really is that we have high viscosities, of course, and therefore also more stress in the whole material conveying system, so we had to tackle this by improving our cartridges and everything basically. So everything that can break broke, and we fixed it and made it stronger, and it helped a lot. Another thing we want to take care of, because we want to build really large parts as these insulation panels, is to look into having the cross-linking of the binders happening between the fibers right after printing. So we want to print, once it's placed on the part or on the build platform, that it starts cross-linking there already. It won't get completely hard, but have it at least become a little more viscous, a little firmer, that it doesn't collapse on its own weight. To do so, we thought of basically a mixing extruder, where we can have the catalyst and the biofiber and binder already pre-mixed, and then mix it right before we place it, or we push it through the nozzle, that it already starts solidifying right after printing on the part. And it would be really awesome if you could add more additives, such as dyes and other additives as needed. So we came up with a design for that, for 4 or more materials as an input, and we wanted also, or we needed to have this, for this to have also high pressure capacities, and it should be easy to dismantle because it's not as sticky anymore, but it's still sticky. And here you can see that in action. This is experimental print head. Here we mixed 2 clays, white clays with dye, red and blue. And you can see there a nice purple color coming out at the bottom, so that worked fairly well. And we also looked into different designs of screws, because they have 2 jobs. One is to push the material out of the small nozzle, and the other one is to mix the sometimes longer fibers well with the catalyst and binder. So we can interchange them depending also a bit on the size of the fibers, for example. All right. Now we have a material that prints fairly well. We have a print head that can print this material. What else is needed to produce big insulation panels for housing, for example? We need a big printer. We settled for now on a build volume of 1.5 by 1.5 by 2 meters, so 4.5 cubic meters, which is, by the way, I find our printers already fairly big. I mean, they have to produce urns, but 50 times more than what we are used to. And that means the printer that has to be built is even bigger than that. And another challenge we found very early is that the material, once it's placed, of course, it starts already to cross-link and starts to become a bit firmer, but we cannot remove it that easily out of the machine. You cannot just grab it and take it out. It will disintegrate in your hands because it's not cured and dried yet. So to tackle that, instead of taking it out, we designed our printer as a porter gantry design, so it's on wheels, which you can lock, of course, and level. So we can print directly on the ground or on a stationary build platform, and then basically the printer gets pushed over the part stays put, and we print another part right next to it. That's the most logical solution. And everything is designed with ball screws, and we wanted it to be as rigid as possible and as stiff as possible, and with minimal backlash, because speed is not our main concern, because the paste cannot be extruded that fast anyway. This is not just a concept. I'm building that printer right now. It is already set up. Everything is mounted, and I'm in wiring right now, and it's wiring hell, but I'm confident that it will start moving and printing still this year. Quick summary on the material itself. We have a clay-like printing behavior we could achieve. Drying usually takes about 2 days. It depends a bit on the thickness of the material, but we can speed up the process by a lot by just applying heat, 100 degrees here, for example, 4 hours for a sample part. Tensile strength and Young's modulus is not great yet. I would compare this to firm-ish XPS foam, but this is also a sample with a fiber volume fraction of 30%, and we achieved to print with higher volume fractions of 45 to 50%, which made the parts much, much stronger. And also thermal conductivity is all right, but it's not as well as we wanted. So next steps is to look into designs of large-scale panels and improve especially the thermal insulation through design and foaming. Okay, and then the last slide.
Last slide comes from me. You can see here the authors of this presentation and the paper in the booklet. And the project partners comes from the chemistry and engineering like GNS, the Additivum GmbH from here with the 3D printing. Then we have also the Institute of Printing and Science from the TU Darmstadt. With the properties to make the properties, and then we have also lithium designs which makes the application, and it is a founding project from government. Thank you for your
thank you very much.
Yeah, thank you. So, questions. Okay, we start in the first row and then we go back to the other row. No, not yet.
We have these samples also in the exhibition, I think.
Not yet, but I have to bring them down.
We had conversations. First of all, thank you. It was super
Pleasure.
nice also to see these different partners coming together to come up with something new, and that there's knowledge in one material and processing that, which then travels to another material. That's amazing. When we saw the mycelium in the morning, we talked about the smell. Yeah.
What does it remind you of?
Cork.
Linseed oil, I find.
I think you know the linoleum.
Yeah.
It is a bit of this.
Yeah.
A bit.
Linseed oil.
Also.
Yeah. So
It doesn't smell like
it smells
it's
familiar.
supposed to
Philip, you talked about familiarity and the wood that smells in a certain way.
And by the way, this is
Linoleum,
also the one with way more fiber content, so that's way better than XPS foam. If you want, you can try to stand on it, I guess.
The
This is
biogas,
okay.
the biogas fibers don't smell because they are cleaned.
Yeah.
This is more the oil with this smells.
Okay, then a question from my side for the urn. Is it fired or is it unfired?
It is fired, but not at the highest temperature for that material. So this is bisque fired. So it will dissolve in water, but after a couple of weeks, months. So especially in Germany, you have to fulfill requirements that everything that goes into a grave either comes out of it again in one piece or is disintegrates basically, and after 2 years they have to dissolve, and they do that. We have to guarantee that. So yeah, they're fired, but just at 900, 850 degrees.
But you had quartz transition already at 670-ish?
Not entirely, no. That's the thing. They did like deep dried, let's say, but they will disintegrate, and they're not. There's no transition yet.
Yeah. Okay.
But stable enough for the whole handling beforehand, because that would be
that would have been a mess.
difficult.
Yeah. Anyone else? Can you pause it?
So just to make sure, because we're talking about firing, but the bio-based one is just dried, right?
We dry them, but we can accelerate the process by a lot. So the idea is not to do that, to just save energy. But so it dries at room temperature, depending on the thickness, but it does it on itself. Like these were not fired or heated up even. We just left them in a room for 2 days, or now a couple of days. But you can speed up the process if you want to, yeah.
Right, thank you.
All right. No more hands? Everybody's so keen for the coffee break, I guess. So, thank you very much. One more applause.